Hi, my name's Brittany and I'm currently a student at the University of New England studying a Bachelor of Clinical Exercise Physiology. This presentation is part of an assignment for the unit EXSC 335, which is a unit on motor control and human development, and is coordinated by Dr Domonic McNeil. So this presentation is in regards to the speed accuracy trade-off. Now, all of the information that comes out of this presentation is generally summed up in this textbook, which is the textbook for our unit. It's by Shumway and Woolacott, and some other information also comes from peer-reviewed journals or lit reviews, that were found online. So the aim of this lab was to investigate the relationship between speed and accuracy by using both spatial and assembly tasks. So firstly, we should probably start off with what the speed accuracy trade-off actually is. So the speed accuracy trade-off revolves around something called Fitz's law. Now, Fitz's law is stated that it's a logarithmic relationship between the duration of reaching the movement and the ratio of movement amplitude and target size. So therefore it said that the slower responses tend to be more accurate than faster responses. In a study by Donkin, Little and Hoop, it's concluded that differences in one variable often can't be interpreted without ensuring that it's not also changing the other variables. So simply, when accuracy is seen to improve, we have to make sure that it's not just a result of the individual slowing down. So Shumway, Cook and Woolacott conclude that the increase in this movement time, which also increases with distance and accuracy, can be partially due to the restraints of our visual system. In a study by Crossman and Goodeve, it's suggested that the relationship between both external or visual feedback and internal, which is proprioceptive or kinesthetic feedback, could actually be the major reason for indicating the multiple types of inaccuracy in movements and be responsible for the intermittent changes that we make to try and correct those movements. So visual feedback is an essential part of motor programming as it gives us a reference point from the external feedback so that we can then apply changes to our movements to better our performance. So, as said, if we make mistakes, our visual feedback allows us to correct them. So, according to Alexandrov, all voluntary movement is based upon open and closed loop control systems. So, Spittle defines open loop control as the initial movement instruction that contains all essential information for that movement to be carried out. Open loop control does not use feedback during movement execution, meaning that the movement cannot be modified once you've started it, and it remains those movements to pretty much be revolving around speed. So open loop control feedback is essentially the fastest type of movement as you're not changing any movements. He also defines closed loop control as sensory information, and it's used to initiate movement and make modifications during the movement progression. This is possible as the initial commands only contain information on how to begin the movement. So when we first learn a movement, we are primarily using closed loop control. So as we become faster, then we can transfer over to open loop control once the motor program has imprinted itself in our brains, so to speak. These are responsible when considering adjustments that require either slowing down at the end of the movement or anticipating how to pick up a pen or make configurations in advance using appropriate speeds for the actions that follow. Now, according to Bate, there are two types of motor theory controls. So the first one is a hierarchical theory or a top-down theory, such as, it's called the motor program theory. Now, this works on the theory that all instructions start from the CNS or the central nervous system, which start at the top of the brain and work their way down through the bottom of the brain through the spinal cord. This control process is managed by a motor program, which then organizes, initiates, and carries out all of these intended actions. The adaptive control of complex movements are performed by the cortex, as well as emphasizing control of movement by knowledge and accumulated through experience and intention, whilst also assuming internal structures changing with learning. So on the other hand, we have the dynamic system theory, which are instructions that are based on feedback from the environment. So this includes this includes interactions between the body and the limb and the nervous system. Now, groupings of these muscles are said to be set in particular properties, which will enable them to interact mechanically with the forces of the environment. Now, the motor program theory is primarily used as it's a hierarchical model and it has a command-based center. Okay, so moving on to the method. So this particular lab had two different tasks that we had to complete. The first was a throwing task, which was to investigate spatial accuracy. So it involved participants standing 3 meters away from a circular target that was glued to the wall. The participants were to complete 10 trials of underarm throwing at 3 different color zones, which were indicative of small, medium, and large. The time between the ball leaving the participant's hand and hitting the target was recorded. The aim of the experiment was to get a score as high as possible by hitting the target accurately in the shortest amount of time. The second task that we had to do was completing 3 trials of a perdued pegboard, which is shown on the screen, which required picking up a pin and putting it into a corresponding hole in the correct order under 3 different conditions. The first was using both hands, the second was using just your preferred hand, and lastly was just using your non-preferred hand. So participants were to put as many pins on the board as they could in 30 seconds, and the aim was to put as many pins in that board in that time as possible. Okay, so from these tasks, we got some results, which I'm going to show to you on a series of graphs and use those to help explain the results to you. So the first one we're going to look at, or the first 2 graphs, we're going to look at are in regards to the throwing task. So the first graph I'm going to show you, which will come up now, is the score out of 10. So the score out of 10 in regards to the throwing task, we can see that the small target had the lowest score out of 10 with approximately 6.8 hits. The medium had the second lowest at about 7.7, and the large had the highest with 7.9 hits out of 10. So through this, we can see that as the target size increases, the average number of hits also increases. So this can be attributed to the larger surface area. So the second graph I'm going to show you is in concern to the average time it took to get the tennis ball to the target. So it is seen to be approximately 0.48 seconds for the small target. It goes down to 0.45 on the medium. And then for the small target, it goes down further to 0.3 to the large target, So through the graph, a near linear decline can be seen with the increasing size of the target. So therefore, the larger the target, the smaller the time to hit the target is going to be, because we don't need to stop to be as accurate as what we would have to be with a smaller target. Now, the third graph I'm about to show you is in concern to the average number of pegs we could get into the Purdue pegboard in that 30 seconds. So the average number of pins inserted was the greatest for when both of the hands were used, with approximately 16 pins. Then the second highest score was the preferred hand, so we can see that has approximately an average of about 13. And finally, down to the smallest amount of pins, which was inserted for the non-preferred limb. So what we can determine from this is that we are far more accurate with both of our hands. Now, this could be because we are using 2 separate entities. We both have a motor program which can work together by increasing the speed. Now, both of the results that we found in today's labs, or the lab, both support the current research that is available in regards to speed accuracy trade-off, in that we need to compromise accuracy for speed or vice versa. So we can see that the participants were able to use their visual abilities in order to give themselves some feedback and then implement closed loop control so that they could fix their movements and then improve the efficiency of their performance. Now, the speed accuracy trade-off is seen in everyday life. It's seen all around us in sporting. In a sporting context, it's very important, as many athletes are needed and they're faced with challenges to require the ability to come up with whether accuracy or speed is more important in a limited time frame. So, for example, in a soccer game, a player is running up with the ball and wants to score a goal. They need to make a decision as to whether they want speed to decrease the risk of the goalie stopping the ball, or if they want to forget about speed a little bit and increase accuracy, which requires them to slow the speed but this also increases the chance of not only getting the goal, but also of the goalie catching the ball. Now, in everyday life, these can be seen in examples such as the keyboard on your computer. So the spacebar is deliberately made bigger so that you can type faster and more accurately without making any mistakes. Now, in regards to the pegboard and the skills attained through an assembly task, things such as putting a key in a lock or picking up a pencil and reorientating it in your hand to be able to write words are all essential parts of everyday life that require the speed-accuracy trade-off. So through this lab, we can assume that in order to have the best possible outcome in performance, spatial accuracy tasks should be started off at slower speeds so that the pattern and basic skill movements can be learnt first. So then once they have been mastered, the basic movement patterns can have speed added to them and therefore move over to open control, which allows them to be more accurate and more speedy than what they would be if you were just learning. Okay, so as for the pegboard, the dominant hand could be used first to practice the movements and get the basic motor control underway. And then as the movement pattern blueprint will then be present in the brain, it can then be transferred over to the non-dominant hand in order to attempt to elicit the same kind of movements. So some limitations to this particular study, firstly, in regards to the throwing task, was that the reaction times of the individuals who were recording the time in which it took from the ball to leave the hand to hit the target on the wall, reaction times differ between individuals. So we used a different individual in every group. This could have been controlled more by using the same participant to record the times, or we could have done a video analysis which we could pinpoint the exact time the ball left the hand to the exact time the ball hit the paper or the target. So another thing was the participants were saying they were getting bored after about the third or fourth throw, which in a way was saying they weren't concerned about the accuracy or the speed so much, they just kind of wanted to get the task done. So the one final factor that probably skewed the data a little bit was some individuals decided they wanted to throw overarm instead of underarm, which changes the muscle control completely. So overarm is more of an accurate and fast throw, so uses a whole set of different muscles in general. The pegboard, some limitations there. The participants were all sitting on the ground. So we had some participants leaning over the pegboard, some kneeling over it, some leaning back. We could have perhaps controlled this a little bit better in order to make it a little bit more reliable by having all of the participants, say, sit at a table or something that they were all in the exact same frame when they were attempting the pegboard, just to make it the experiment that little bit more reliable. So some future research in this area, in particular to this lab, could be directed as to whether there is an order effect present in regards to the throwing task. Some participants started off with the smaller targets and moved their way up to the large targets, and some participants started off with the large targets and worked their way down to the small targets. So there could be it would be interesting to see if there was an effect in the central nervous system as to whether this order effect makes a difference in accuracy or speed. Thank you very much for watching my presentation. I hope you enjoyed it and I hope that you learned something out of it, and I hope it was fun for you. Thank you.